Welcome to this explainer. Today we're going to shatter the illusion that Python alone is doing the heavy lifting in artificial intelligence. If you follow modern tech trends, it's so easy to believe that AI is entirely built on Python. It's the elegant, super developer-friendly interface behind pretty much all your favorite AI tools, apps, and websites. But today, we're peeling back that shiny outer layer to reveal the brutal, high-performance mechanical underbelly that actually makes modern computation possible. Let's dive in.
If you've ever built an AI model or even just followed a quick tutorial, you've definitely typed a familiar magic incantation like this. And honestly, you probably assumed Python was the one running the whole show. Every piece of framework documentation and every open-source generative AI tool seems to start exactly this way. It is literally everywhere, so it totally makes sense why the Python runs AI myth is so pervasive. But that raises a critical question for us. What is actually happening underneath that clean, developer-friendly syntax? When you write a simple line of code to execute backpropagation, is Python actually doing the math? The short answer? Absolutely not. Python is basically just acting as a switchboard operator, happily handing over data pointers to something far, far more powerful.
Okay, Section 1, the great AI illusion, beyond the Python facade.
To really grasp this illusion, we have to look at the architectural friction that makes it functionally impossible for Python to handle raw AI workloads on its own. Deep learning is defined by massive scale and an uncompromising demand for compute power. And you hit immediate roadblocks relying solely on Python. Look, Python is fantastic for developer speed, but its global interpreter lock and its automated garbage collection, they make it practically impossible to handle the raw, multi-threaded computation that deep learning demands. The GIL literally prevents multiple native threads from executing Python bytecodes all at once. And think about it. Training an AI model requires massive parallel computation across dozens of CPU and GPU cores simultaneously. Throw in Python's garbage collection, which introduces these arbitrary pauses and completely unpredictable latency right when you're trying to shift gigabytes of matrix arrays, and you've got a system that simply cannot keep up natively.
Moving on to Section 2, C++, the hidden engine powering AI's underbelly.
So, let's finally pull back the curtain and look at that roaring engine. If Python isn't doing the math, what on earth is? The answer lies in compiled systems languages, specifically C++. C++ bypasses Python's limitations entirely. It gives developers absolute control over memory management, letting them orchestrate precise multi-threaded execution paths right down to the physical silicon. To put that into perspective, check out this shocking statistic. Empirical benchmarking shows Python is over 300 times slower than C++ when executing AI algorithms from scratch. A recent study implemented 5 core AI algorithms, everything from neural networks to genetic algorithms, across 6 different languages just to test native execution speed. Without the help of optimized external libraries, Python sat at a staggering 315 times slower than C.
And when we map that execution time across those 6 languages, the reality becomes pretty stark. At the highest performance tier, C, C++, and Rust are virtually indistinguishable down at the bottom. They are blazingly fast. Meanwhile, Python's bar just stretches way up into the stratosphere, whether it's executing arithmetic-dense tasks like k-means clustering or branch-heavy stuff like genetic algorithms.
So this hierarchy creates what we can think of as a compute pyramid. Think of Python as just the steering wheel, C++ is your transmission, and CUDA is the physical road connecting it all to the GPU. It's the ultimate symbiosis. You've got Python sitting comfortably at the top for human productivity, C++ forms that high-performance backend, ensuring every single byte is allocated with zero overhead, and then at the base, NVIDIA's CUDA translates those C++ instructions into massively parallel grid executions across thousands of GPU cores.
All right, Section 3, Major AI Frameworks. What's under the hood?
Let's take a look at the tools developers use every single day. Because once you understand this compute pyramid, you really start to see it everywhere. The open-source frameworks that serve as the basic building blocks for modern AI tools, apps, and websites, they're practically all built on this exact same blueprint. Whether you're firing up TensorFlow, PyTorch, MLPack, or OpenCV, these are essentially all just C++ wrappers doing the actual mathematical heavy lifting. Take TensorFlow, for instance. It uses a deferred execution model, where your Python code just builds a graph, but a distributed C++ runtime system is what actually executes it. OpenCV brings decades of pure C++ computer vision processing straight to Python. And MLPack is explicitly a native C++ machine learning library designed specifically for high-performance and edge AI, using C++ to seamlessly integrate with sensors on low-resource devices.
In fact, advanced simulation environments like Moose use libtorch, which is the C++ front end of Python, to bypass Python completely for seamless native reinforcement learning. This is super fascinating because in highly complex simulations, like modeling nuclear materials or advanced thermal hydraulics, traditional file-based communication through Python is just way too slow and error-prone. By linking directly to libtorch, C++ applications can train and evaluate artificial neural networks natively. It enables real-time interaction and optimization without the Python middleman.
Which brings us to Section 4, the cost, memory leaks, and why C++ demands precision. You see, all this incredible C++ performance comes with a pretty steep operational cost. C++ doesn't have the luxury of Python's automated garbage collector. It demands absolute precision from the engineer. It provides absolute control, sure, but that means it requires manual memory management. And if you forget to delete memory, you create a memory leak. It's kind of like a worker just leaving finished papers on their desk until there's literally no room left to work. Imagine an office where every completed task just sits there on the desk forever. Eventually, you can't start any new projects. In machine learning, if you forget to free memory that was allocated for processing a tensor, well, that memory is permanently locked away.
And this creates a catastrophic cascade of failure. An unreleased tensor quietly piles up until the system just runs out of memory, and your entire machine learning pipeline abruptly crashes. The scarier part? When things go wrong at this level, they go wrong quietly at first and then entirely catastrophically. This constant shuffling slows down everything from data loading to model inference. Your ultra-fast, high-performance AI model starts operating way below its potential, and eventually, the application just flat-out runs out of memory, bringing your crucial operations to an abrupt and very costly halt.
Let's move to Section 5, AI on the web, C++ beyond the server. So, with all this complexity, you might be wondering, is this roaring C++ engine trapped only on massive server farms and supercomputers? It's easy to assume that this kind of low-level, high-performance execution requires dedicated hardware. But the landscape of software engineering has radically shifted. Thanks to WebAssembly, or WASM, these heavy C++ workloads are now being compiled to run with near-native speed directly in your web browser. WASM is this incredible binary format that acts as a secure, insanely fast execution environment. We're talking 1.5 to 20 times faster than standard JavaScript for compute-intensive tasks. And with startup times of literally just 1 to 5 milliseconds, it's pushing C++ capabilities out to edge platforms, serverless functions, and right into the apps and websites you use every single day.
This combination of C++ and WebAssembly is already powering massive browser apps like Figma, Photoshop, and Google Earth, proving that the true engine of AI really can run almost anywhere. And these aren't just obscure edge cases, right? These are major industry-standard tools running C++ natively in the browser right now. By compiling decades of legacy C++ code into WASM, Adobe actually brought full Photoshop capabilities to the web without having to start from scratch. Figma migrated its C++ rendering engine to WASM and saw load times plummet by 3 times. It's a real game changer. The massive power of C++ is just no longer confined to back-end servers.
Ultimately, it's a beautiful symbiosis. It perfectly captures the engineering compromise that drives modern artificial intelligence. We really don't have to choose between the rapid prototyping capabilities of Python and the blistering execution speeds of C++. Instead, we just layer them. We get the very best of both worlds, and that's exactly what's driving the incredible pace of AI advancement we're all witnessing today. Well, this brings us to the end of our explainer. But I want to leave you with one final provocative thought. Now that you actually know what's humming under the hood, what will you build with the true engine of AI? Are you going to write native C++ optimizations for edge devices? Or maybe leverage WebAssembly to bring heavy machine learning models right into the browser? The potential is absolutely limitless once you understand the real tools you have at your disposal. Thanks so much for joining me on this deep dive, and I'll see you next time.